Okay, starting from the lecture. So today is lecture number 23, which is from chapter number 17, compressible flow. So in the previous class, we already discussed about compressible flow, what is the difference between compressible and incompressible flow, and how you have to judge that whether your flow is compressible and incompressible. So the dimensionless number which we have to use for identification of the compressible flow is the Mach number. So Mach number, if greater than 0.3, it is defined as a compressible flow. If it is less than 0.3, it is incompressible flow. Okay, and we already developed one equation which is for speed of sound for the isentropic condition. Okay, so now we will just try to solve some questions which are related to speed of sound. Okay, and this is just a quick overview that we already developed one equation for speed of sound by using this type of piston cylinder arrangement. Okay, and then these are the equation which we already see in the previous lecture. Okay, so speed of sound, you can say that it is k partial p by partial rho. Then this equation we have already derived, c is equal to kRt. So if the temperature is known to you, you can easily find the speed of sound in any medium. Okay, and then this is the Mach number, which is a ratio of local velocity to speed of sound. Okay, and from this figure, if you can see, this is on your right side. Uh, this is just an example that how your speed of sound vary in different mediums. So for example, in one case there is air, and at 200 Kelvin, the speed of sound is 284 meter per second. Similar case, if we have helium at same temperature, the speed of sound become 832 meter per second. So first thing, from this example you can easily judge that with the change of medium, speed of sound changes. Then if you can notice that with the increase in temperature, so as the temperature is increasing, so again we get the increase in speed of sound. Okay, so this is because if you can see this relation, c is equal to k RT, so it is directly proportional to speed of sound is directly proportional to the temperature. Okay, so this is just for your understanding purpose. And then this is another example. So if here there is an example that an aircraft is flying at some altitude. Okay, so in first case we can say it is at the higher altitude, because if you can notice, air temperature is low. Okay, so at higher altitude its mean temperature is lower. In second case we can say that temperature is 300 Kelvin and it is flying, the aircraft is flying at the lower altitude as comparison to the above case, and the speed of aircraft is same, 320 meter per second for both of the cases. And if you can notice that the Mach number at higher altitude or at lower temperature is higher as comparison to the lower altitude or higher temperature, okay, which is 0.92. Okay, so this is how your Mach number vary, that it will increase as your altitude increases or as your temperature decreases. Okay, so this is just for example, and here we already discussed that how you characterize different compressible flows. Okay, so if it is Mach number is equal to 1, it is sonic flow. Mach number less than 1, subsonic flow. Greater than 1, supersonic flow. And then we already discussed what are the ranges where we have to specify different type of compressible flows, hypersonic flow, and then this is the transonic flow. Okay, so this we will discuss when we are going to solve the problems as well, that how you can figure it out that your flow regime, your flow condition are subsonic or supersonic flows. Okay, so here there is an example which is related to the speed of sound. Okay, so this is example 17-2 from your book. So 17-1 we will discuss in the coming slides. Okay, so first you have to read the statement. Okay, so air enters a diffuser shown in this figure with a velocity of 200 meter per second. So you have to determine speed of sound and Mach number of diffuser inlet when air temperature is 30 degrees Celsius. Okay, so this is your question. Okay, so you have to note it down the required data, and then we will see how to solve it. Okay, so in the part A, we have to find the speed of sound. So C is equal to under root KRT. So simple equation. So value of K for air, you already know 1.4. Gas constant for air, the value is 0.287 kilojoule per kg dot Kelvin, and the temperature is mentioned in the question, which is 303 Kelvin. Okay, so simply you have to put the values and you will get the speed of sound easily. 1.4. Okay, here you have to convert into joule per kg dot Kelvin, because if you cannot do the conversion, it will give you the wrong units. So here we convert into 287, which is joule per kg dot Kelvin, and this is 303 Kelvin. Okay, and if you can solve it, you will get the value of C, which is 349 meter per second. So in part B, simply we have to find the Mach number. So Mach number is basically local velocity over speed of sound. So local velocity is 200 meter per second, which is mentioned in the question. Okay, which is at the diffuser inlet, and then C is we already calculated, which is 349, and if you can calculate it, it will be 0.573, and this value is less than 1. Okay, so it's mean that your uh, type of compressible flow is subsonic flow, because Mach number is less than 1. Okay, so this is the solution for this type of question. If you have any question, you can ask me, or you can note it down and then move towards the next question. Okay, so coming towards the next question, which is from your book, and it is 17-20 from the end of your book problems, which is mentioned at your end of the book. Okay, so the carbon dioxide enter an adiabatic nozzle at 1200 Kelvin with a velocity of 50 meter per second and leave at 400 Kelvin. So the nozzle inlet condition and outlet temperature is known to us. Okay, so temperature at inlet is mentioned, and pressure at inlet is mentioned, and temperature at outlet is mentioned, and the working fluid is carbon dioxide. Assuming constant specific heat at room temperature, so you have to determine Mach number at inlet and at exit of the nozzle. Okay, so it is a very simple question. So you have to note down the data and then we will see how to solve it. Okay, so I will just draw one nozzle. Okay, so this is just a nozzle, and carbon dioxide is the fluid, and 1200 Kelvin at inlet, and 50 meter per second is the velocity, and 400 Kelvin at outlet. Okay, so in part A, simple, we have to find the Mach number at inlet. Okay, so Mach number is basically, so we can say this is point number 1 and this is point number 2. So Mach number 1 is V1 over C1. So V1 is mentioned in the question, which is 50 meter per second, and C1 we have to find. So first we can find the C1, so KRT, and K value for the carbon dioxide you can easily find from thermodynamic table A2. Okay, so K value is 1.288. Gas constant for carbon dioxide is 188.9. This is in joule per kg dot Kelvin. Okay, and then 1200 Kelvin. So if you can take the under root over there, and then it will be 540.4 meter per second. So now the Mach number 1 become 50 divided by 540.4, and now here we get the value, which is 0.0925. Coming toward part number B. Okay, so in part number B we have to find Mach number at the exit of the nozzle. So here we do not have the value of local velocity at point number 2. Okay, so first thing we have to find the local velocity, which is at point number 2, which is V2. Okay, so simply you have to apply steady flow energy equation. The steady flow energy equation basically it is that H2 plus V2 square divided by 2 is equal to H1 plus V1 square divided by 2. Okay, so this is the basic energy steady flow energy equation. Okay, so from here if we can just simplify it, so it will be equal to 0 is equal to H2 minus H1 plus V2 square divided by V2 square minus V1 square divided by 2. Okay, so this is just a simplified version of this, and from there H2 minus H1 we can easily write delta H is equal to Cp delta T. Okay, so now we can replace this H2 minus H1 with Cp delta T. So you have to note it down, and then we will just go to next slide, and then we will solve further question. Okay, so if we can just put the value of H2 minus H1, so the equation becomes Cp T2 minus T1 plus V2 square minus V1 square divided by 2. Okay, so we have the value of Cp from thermodynamic table. T2 value is known to us, T1 value is known to us, V1 value is known to us. Okay, and if you can solve for V2, so you have to solve it by yourself. So V2 is equal to 1163 meter per second. Okay, so now we can easily find the Mach number. Okay, but we need value of C2 as well. Okay, so C2 is equal to K2 R T2. Okay, so K is basically the same thing because carbon dioxide is the fluid. So 1.288, gas constant is 1.8.9, and then this is 400 Kelvin. So here we get the value of C2, which is 312 meter per second, and from here we can easily find Mach number at 2, which is at the exit of the nozzle, and V2 divided by C2, and now you can put 1163 divided by 312, which is equal to 3.73. Okay, so this is the required thing, which is we have to find the Mach number at the exit of the nozzle in part B. So if you have any question, you can ask me, and then we will move to the next one. Okay, so now coming towards the next topic, which is stagnation properties. Okay, so I hope you already know this term, stagnation, from your fluid mechanics course. Okay, so what is the definition of stagnation point? So it is a very simple definition that the point on the immersed body where the velocity is zero is called stagnation point. Okay, so any body which is immersed, for example, if there is an aircraft showing on this picture, so the wing of the aircraft is immersed in air. Okay, so this is the fluid. Okay, and we can say that at the tip of the wing or at any point over the wing, we call it as a stagnation point where the velocity is zero. Okay, so this is the simple definition, and this is the velocity of the air. Okay, so here, okay, stagnation point, and any point, any property which is on the stagnation point, we define as the stagnation property. So for example, for thermodynamic analysis purpose, I can say you have to find your pressure, temperature, enthalpy at the point where the velocity is zero. Okay, so you can simply say that you can denote T naught. So sometimes we denote as T naught, H naught, U naught, P naught as a stagnation point. And in some books we have TS, HS, US, or PS. Okay, so do not confuse these terms. So if it is mentioned in the problem statement that the point where you have to do the thermodynamic analysis is the stagnation point, so it's mean the velocity is zero at that point. Okay, and why we are interested in to find the stagnation properties? Okay, because if this is the point where all your kinetic energy is converted into internal energy, okay, at the stagnation point. Okay, so that's why most of our thermodynamic properties, as a thermodynamic, if you want to perform thermodynamic analysis or the temperature distribution analysis, so your most concerned part is at the stagnation point. Okay, so that's why we have to look into stagnation properties. Okay, so now coming towards some derivation in order to find the stagnation properties. Okay, it will be used in further problem analysis as well. Okay, so you have to just carefully see how to develop these equations. Okay, so for example, I just take one wall. Okay, just for an example. Okay, and the flow is coming towards it, and at the wall I can just say that this point is the stagnation point. Okay, so that can be any area or any location. Okay, so just I will say that this is the stagnation point where the velocity is zero. Okay, and I can denote this point as S, which is the stagnation point. And here this is the point where the flow is started, and I can define as point O. Okay, and you can say it is a local point. Okay, so now in order to develop some properties at the stagnation, in order to define some relation, in order to find the properties at stagnation point, so first thing we have to apply Bernoulli equation. Okay, so Bernoulli equation, I hope you already know. Okay, if you have to apply a Bernoulli equation between 2 points, so it becomes, so for example, P naught rho g V naught square by 2g plus Z naught is equal to Ts, which is a stagnation pressure, rho g plus stagnation point 0 square 2g plus Z at stagnation. Okay, so here another assumption you can say that these 2 points are on the same height. Okay, so it's mean we can eliminate this Z from here, and you already noticed from the definition of the stagnation point that at stagnation point velocity is zero. So Vs is equal to zero. The stagnation point velocity is zero. So if we can further simplify this equation, so this equation become P naught divided by rho g plus V naught squared divided by 2g is equal to Ps divided by rho g. Okay, so this is the simplified version of the Bernoulli equation for stagnation point. Okay, so now if I can further simplify it by just dividing both sides with P naught divided by rho g. Okay, so the equation become Ps divided by P naught is equal to 1 plus rho V naught square divided by 2 P naught. Okay, so this is the equation, and if I can say that this equation is Ps equal to P naught plus rho V naught square divided by 2. Okay, so this is I can also write in this way. Okay, so from here, if you can figure it out from this equation, that the pressure at your stagnation point is higher as comparison to the pressure at point O, where the flow is started, by the term rho V naught square divided by 2. Okay, so it's mean that always you will get stagnation pressure higher as comparison to the pressure at your point number O. That will be from this equation. Okay, so you have to note down this equation because this is an important equation which we have to use for further analysis. If you have any question, you can also ask me.
सर ये प्रेशर एट पॉइंट तो वही स्टैटिक प्रेशर है हमारा
जी आपका स्टैटिक प्रेशर होगा.
ओके
Okay, so now in the second stage, again the point is O, which is our starting point, or you can say local point, and then this is the stagnation point where your velocity is 0. Okay, so now we have to apply steady flow energy equation between these 2 points. So steady flow energy equation, you already know that enthalpy at point O, kinetic energy at point O, potential energy at point O plus heat transfer is equal to enthalpy at stagnation point, and this enthalpy is in kilojoule, not in per unit mass. So kinetic energy at stagnation point, potential energy at stagnation point plus W. So this is the general steady flow energy equation between these 2 points. Okay, so from here we already know that there is no height difference, so potential energy eliminated over there. There is no heat transfer because it is adiabatic, and so there is no heat transfer. There is no transfer of work, so W term is sorry, is also eliminated from here. Okay, so now if I can write this equation as in per unit mass, so it will be H naught V naught square divided by 2 is equal to stagnation enthalpy per unit mass plus Vs square divided by 2. Again, stagnation velocity is 0. So we can say that your enthalpy at stagnation point is equal to sum of enthalpy at the local. Okay, so it is the enthalpy at the point O plus V naught square divided by 2. So again, your enthalpy at stagnation point is higher as comparison to the enthalpy at point O by the term V naught square divided by 2. Okay, so now here, if we can further simplify this equation, and by putting the value of H, which is CPT. So this you already know from the previous lectures. Okay, so I can just put the value Cp Ts is equal to Cp T naught plus V naught square divided by 2. Okay, so now if I can just divide Cp T naught on both sides, so we will see what happens to this equation. So Ts So this term is eliminated, this term is also eliminated. Okay, so you have to note it down. So our final equation become Ts divided by T naught 1 plus V naught square divided by 2 Cp T naught. Okay, so till this point you have to note it down, and then we move towards the next part. So our equation becomes Ts divided by T naught is equal to 1 plus V naught square divided by 2 Cp T naught. So from the previous lecture, Cp value is K into R K minus 1. Okay, so this equation you already know from the previous lecture. So you have to plug the value of Cp in this equation. So our equation becomes Ts divided by T naught 1 plus V naught square divided by 2 Kr, and K minus 1 will be in the numerator as well, and here we have T naught. Okay, so this is our equation now. And now if we can further analysis, simplify this equation. So here we can know that C is equal to under root KRT, and here we can say that C naught square is equal to KR T naught. Okay, so we can say that C naught square is equal to KR T naught. So now we can simply put the value in this equation. To C naught square. So this all effort we are basically trying to do to develop relations of the stagnation pressure with your temperature at the local point and in terms of Mach number as well. Okay, so that we can easily analysis the compressible flows. Okay, in order to find the stagnation properties. So here we can say that Mach number is equal to V naught divided by C naught. So if we can say Mach number at point O, and if we can take the square, so it will be V naught square divided by C naught square. So we can replace this term with Mach naught square. Okay, so I can just put the value over there. So Ts divided by T naught is equal to 1 plus Mach naught square K minus 1 divided by 2. So Ts is equal to T naught 1 plus K minus 1 divided by 2 Mach naught. Okay, so this is the equation by which you can easily find the stagnation temperature. If your temperature at point O or the initial point is known to you, specific heat ratio, the K value of the working fluid is known to you, and Mach number at your point number O is known to you, so you can easily find the stagnation temperature from this equation. So this is an important equation, so you have to note it down, and then we will try to develop some more equation in order to find the stagnation pressure and stagnation density. Okay, so we will take 10 minutes break at this point, and then we will again join to derive further equations. Okay, so starting from again the stagnation temperature. Okay, so the equation which we already developed in the last slide. Okay, so if you already know that the isentropic processes, the relation between any two isentropic points, and for the isentropic process, T2 divided by T1 is equal to P2 divided by P1, K minus 1 divided by K. So this equation you already know from the previous lectures as well, and chapter number 7. So here I can just denote point number 2 as a stagnation point, because these are my 2 points, stagnation point and point O. Ts divided by T naught is equal to Ps divided by P naught K minus 1 divided by, because we are assuming that it is the isentropic process and reversible adiabatic. Okay, so now here if you can simply say that Ps divided by P naught is equal to Ts divided by T naught K divided by K minus 1. So you can easily write equation like this. So if I can put the value of Ts divided by T naught from, you can say this is equation number 1, from 1 into 2. So the equation become 1 plus K minus 1 divided by 2 mat naught square K divided by K minus 1. Okay, so this is your equation for the stagnation pressure. Okay, so if you know the value of P naught, and if you know the Mach number value and specific heat ratio value for the working fluid, so you can easily find the stagnation pressure by using this relation. So this is another important relation, so you can say it is equation number 3. So you have to note it down, and then you develop another relation for finding the density as well. So similarly, you already know another relation, T2 divided by T1, rho 2 divided by rho 1, K minus 1. Okay, so I hope you already know this relation as well. So here I can write stagnation density, or density at point O, which will be equal to stagnation temperature divided by temperature at point O, 1 divided by K minus 1. Okay, so I can easily write this equation as well. So simply I have to put again Ts divided by T naught value in this equation. So rho s divided by rho naught is equal to 1 minus K minus 1 divided by 2 Mach naught square and 1 divided by K minus 1. So this is another equation which we have to use in order to find the stagnation density. If we know the value of density at point O, and we know the Mach number and specific heat ratio for the fluid. Okay, so these are important equations, so you have to note it down, and then we will apply these equations in order to solve some problems as well. If you have any question, you can also ask. Okay, so these I already explained to you how to apply energy balance equation, and then how to develop this equation, which is the enthalpy or stagnation point, and then okay, so these are the same things which I already explained to you. Okay, and this is again the same thing. Okay, so this is another important point over there is, okay, the stagnation state is called isentropic stagnation state when the stagnation process is reversible as well as adiabatic. Okay, so we define as the isentropic stagnation. So entropy of fluid remain constant during an isentropic stagnation process. However, if we compare the actual with the isentropic stagnation state, so if we can say that this is point number one, so this is your 2s for example, so which is the isentropic stagnation point, which is 2s. So similarly, if I can say the actual stagnation point, so it is towards the increase in entropy, so this is s, so it will be increase. Okay, however, if we can note from HS diagram, the enthalpy at point 2s, it is the isentropic point, and the actual point is equal. Okay, so what is the reason behind it? Why these two enthalpies are equal? The reason is because also the actual process we are taking as a adiabatic over there, because this is the stagnation point. Okay, so it's mean the velocity is zero. Okay, so we can also say there will be q is equal to zero, and by defining the adiabatic process for both of the cases, isentropic or it is for the actual. If we say that it is not a adiabatic, so definitely then the enthalpy will not be equal over there. But if you can also notice that there is two different points, which is pressure. So the pressure at uh, isentropic point is more as comparison to the pressure at actual stagnation state. So why there is a difference between pressure for the actual and isentropic one? So this difference come from the irreversibility, which is from the fluid friction. So in the actual process, there is a fluid friction. So due to this fluid friction, the pressure decreases as comparison to the isentropic stagnation state. If you can look for the actual stagnation state. So in the actual, we get the low pressure due to the fluid friction, and that is due to the irreversibilities. Okay, so same thing explanation which is written over there. The actual stagnation pressure is low than the isentropic stagnation pressure, since entropy increases during the actual stagnation process as a result of fluid friction. Okay, so this is the reason. So this is just a quick overview of how to compare actual with the isentropic stagnation state. So these all equation I have already explained to you. Okay, so you have to go through it by yourself. Okay, and then these are the important relations which we have to use for the problem solving process. Okay, so stagnation temperature, stagnation pressure, and stagnation density. Okay, so here it is written over there gamma, so it is basically specific heat ratio, so do not get confused. That's why it is written that gamma over there. So here we will look into 17-1 example. Okay, so first you have to read the statement. So in this statement it is mentioned an aircraft is flying at a cruising speed of 250 meter per second at an altitude of 5000 meter, where the atmospheric pressure is 54.05 kilopascal and the ambient air temperature is 255.7 Kelvin. The ambient air is first decelerated in a diffuser before it enters the compressor. Assuming both the diffuser and the compressor to be isentropic, so you have to determine two things: stagnation pressure at the compressor inlet and require compressor work per unit mass if stagnation pressure ratio of the compressor is 8. Okay, so this is the question. So you have to note down the data, and then we will see how to solve it. Okay, so if you can look into the figure, so this is point number 1, which is the diffuser inlet. This is 0 1, so this is just for the understanding purpose. That 0 1 means that this is the stagnation points, and this is another stagnation point, which is a point 2. So you can write any numeric value 1 2 3. Okay, just for your convenience purpose. So here it is mentioned that inlet is 1, exit of the diffuser is 0 1, or inlet of the compressor is 0 1, and outlet of the compressor is 0 2. So all the pressures at properties at inlet is known to us. Okay, so for reference purpose, I can say this is point 1, this is point 0.01, and this is point 0.02. Okay, so this is your diffuser inlet, this is diffuser outlet, and this is compressor outlet. So in part A, our main thing is to find stagnation pressure at compressor inlet. So we have to find the properties at point 0.01, which is the pressure. So in order to find the pressure, first we need to find the value of temperature at this point. So you already know the relation, that how to relate stagnation temperature with the local temperature, which is a T1 plus V1 square divided by 2 Cp. Because this equation we already developed in the previous slide as well. So here, if I put the value, because point 1 property, which is temperature, 255.7 plus V1 square is also mentioned, 250 meter per second, and 2 Cp value is 1.005, but it is in kilojoule, so you have to convert into joule. Okay, then you will get the consistent units as well. So if I can solve it, it will be 286.8 Kelvin. So now we have the value of T01. So similarly, uh, our main target is to find pressure. So T01 divided by P1 is equal to T01 divided by P1 K minus 1 K divided by K minus 1. Okay, so this equation we already see in the previous slide as well. So here we can easily find the T01 54.05 and T01 is 286.8. We have just find in the previous section, and then 255.7, and then this is 1.4, 1.4 minus. So if I can solve it, it will be 80.77 kilo Pascal. Okay, so this is our required value. So if you can notice from these value, you can easily judge that at point number 1 we have temperature 255.7 and pressure at point 1 is 54.07. So at the stagnation point, which is 0.1, we get the increase in temperature, and we also get increase in pressure as well. Okay, so which we already discussed in the previous slide, that by using the equation we get increase in temperature by some term. Okay, so this is how we get the increase in temperature. Okay, so if you have any question, you can ask me, and then we will solve the part B as well. Okay, so part B, we have to find the required compressor work. Okay, so compressor work, you can say Wn is equal to H02 minus H01. So compressor is between 02 and 01. Okay, so we can also write Cp T02 minus T01. Okay, which is the compressor work, and this is the work supplied. But here we already have the value of temperature at the compressor inlet, but we have to find temperature at compressor outlet first. So temperature at outlets, we can simply apply, because here it is mentioned that the process is isentropic. So T02 divided by T01 is equal to P02 divided by P01 K minus 1 divided by K. Okay, so, and also it is mentioned from the problem statement that if the stagnation pressure ratio of the compressor is 8, okay, so it's mean that P02 divided by P01 is mentioned in your question, which is 8. So T02 is equal to 286.8 into 8, 1.4 minus 1 divided by 1.4. And if you can solve it, you will get the value, which is 519.5 Kelvin, which is T02. Okay, and further, if we have to find the compressor in, so we can just put the value 1.005, 519.5 minus 286.8, and it will be equal to 233.9 kilojoule per kg. Okay, which is the required thing to find the compressor work in part number B. Okay, so this is the solution for this example. If you have any question, you can ask me, and then we will go towards the next question. Okay, here there is another question. Okay, so this is not from your book, so you have to note down the data. Okay, so an aeroplane is flying at some speed 1000 kilometer per hour through still air, having a pressure of 78.9 kilonewton per meter square. Temperature is mentioned, so you have to calculate the stagnation point properties on the nose. Okay, and the stagnation property which you have to find: stagnation pressure, stagnation temperature, and stagnation density. Okay, so this is the question, so you have to note down the data, then we will see how to solve it. Okay, so coming towards the okay, so the relation first, we already know. In order to find the stagnation pressure, we have already developed one equation, which is PS is equal to P naught 1 plus K minus 1 divided by 2 Mach number naught square divided by power K minus 1. Okay, so this is the equation which we already discussed in the previous slide. Okay, so here we have the value of P naught with us. K we can easily find, but it is A. But first we have to find the Mach number. Okay, so Mach number we can easily find from V naught divided by under root K R T. So V naught is 277 under root 1.4. R value is 287 in joule per. So this is joule per kg dot Kelvin, and T naught value is known to you, which is 265. So if you can solve it, you will get the value of Mach number, which is 0.851. So Mach number at point O is known to us. Okay, so simply you have to plug the value into the equation, and you will get the value of your stagnation pressure, which is 78.5, P naught value, which is from your problem statement, and then 1 plus 1.4 minus 1 divided by 2 to 0.851 square 1.4 divided by 0.4. Okay, so if you can solve it, you will get the value as 126.1 kilonewton per meter square. So this is your value of stagnation pressure for part A. Okay, so you have to note it down, and then we will see how to solve part B.
सर
जी
एक्सक्यूज मी सर
जी 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 बताएं।
सर ये मैक नंबर फाइंड आउट करते हुए वी नोट की वैल्यू 277.775 से 1000 किलोमीटर पर आवर दी हुई
1000 किलोमीटर पर आवर थी ना, उसको आपने मीटर पर सेकंड पे कन्वर्ट कर दिया। ये मीटर पर सेकंड है ना दोनों जी।
सर आपकी आवाज़ नहीं आ रही, बहुत कट रही है।
सबको मसला आ रहा है, किसी एक स्टूडेंट को नहीं आ रही? आपकी मेरे ख्याल से आवाज़ में बहुत नॉइस है पीछे।
सर हमें क्लियर आ रही है।
मेरे ख्याल से आप कहीं ट्रैवल कर रहे हैं उस टाइम, इसलिए आपको आवाज़ थोड़ा सा इशू आ रहा है। मैं आपको बता देता हूँ कि हमारे पास जो वैल्यू थी प्रॉब्लम में, वो 1000 किलोमीटर पर आवर थी। ओके, तो हमने क्या करना है, मीटर पर सेकंड में लेके जाना है, क्योंकि आपके पास वी नॉट की वैल्यू मीटर पर सेकंड में है, सी की वैल्यू मीटर पर सेकंड में है। सो दैट्स व्हाई यू हैव टू मेक इट कंसिस्टेंट, और ईदर यू कैन मेक द वैल्यू ऑफ सी व्हिच इज स्पीड ऑफ साउंड इन किलोमीटर पर आवर, okay, and keep it the v naught value same as 1000 kilometer per hour. Okay, so that's why I have to do the conversion. I hope you all know that how to convert kilometer per hour into meter per second.
जी सर।
Okay, so coming towards part number 2, or you can say B, so where we have to find the stagnation temperature. So stagnation temperature, again, the same relation which we already developed, 1 plus k minus 1 divided by 2 Mach naught square. Okay, so this is the relation. So T naught value is known to you, and then Mach number naught we already find. Okay, so simply you have to plug all the value, and you will get the stagnation temperature as. Okay, so you have to solve it by yourself. So I'm just going to write the answer, which is 303.4 Kelvin. Okay, simply you have to solve it, and you will get the stagnation temperature. So in the 3, or the stagnation density we have to find, so rho s is equal to find. Okay, so we cannot simply use the relation which we already developed for the stagnation density, because in that relation we have to find the stagnation density at point O as well, okay, which is the starting point. So rather than this, we can simply apply the ideal gas relation. So P stagnation is equal to rho stagnation R into T stagnation. Okay, so I have just make it all stagnation point. So we have the value of T stagnation with us. So gas constant you can get from the thermodynamic table, and T stagnation we already found in the part B. So if you can solve it, you will find the stagnation density value, which is equal to Ps divided by Rts. So Ps, which will come from part 1, which is 126.1 kilonewton. So you have to convert into Newton per meter. Then R value is 287. and 303.4 Kelvin. So now here we have the stagnation density 1.448 kilogram per meter cube. Okay, so this is the third part. Okay, so now solution is complete. So you have to note it down. If you have any question, you can also ask me. Okay, so coming towards the next question. Okay, so this is the last question for this lecture. Okay, so in aircraft flying at an altitude where the pressure was 35 kilopascal. Okay, so our local pressure is known to us. Okay, so it can be from the initial point, and then the temperature at the initial point is also known to us, minus 38 degrees Celsius. Stagnation pressure is also mentioned in the question. Okay, so in the previous cases we have to find the stagnation pressure. Now the stagnation pressure is known to us. So you have to calculate the speed of the aircraft, which is the local speed. Then take molecular weight of air as 28. Okay, so this is the question. Okay, so now we will see how to solve it. Okay, so in order to solve it, our main target is find the speed of aircraft. Okay, so from the relation you already know, stagnation pressure is equal to pressure at the local point, which is at the starting point, plus rho naught v square divided by 2. Okay, so this equation we have already developed in the previous slides as well. Okay, so our main interest is to find this value, which is v. Okay, so here we have the value of, sorry, this is rho naught, okay, not p naught. So we have the value of p naught with us, which come from here, 35 kilopascal. Okay, so rho naught value we have to find. Okay, and stagnation pressure is also known to us. Okay, so first thing we have to find for the rho naught value. So simply you have to apply ideal gas relation. PV is equal to m r t naught, and from here, if you can make p naught v m, and you can change gas constant by using this relation, which is the universal gas constant over molecular weight. Okay, so this equation we chapter as well. Okay, so Ru value is the universal gas constant, which you get from thermodynamic table. Okay, so if I can further simplify it, so here we get the m divided by v is equal to p naught molecular weight universal gas constant divided by t naught. So we already know m divided by v is basically density. So this is rho naught. Okay, so from here we have to find the rho naught first. Okay, so rho naught value come from here by using all the required thing, which is 35 into 10 raised to power 3 pressure from question data. 28 is also mentioned in the problem statement. 8314 is the gas constant, and 235 is the temperature. So if you can solve it, you will get 0.5 kg per meter cube. So this is the value of rho naught. Okay, so simply you have to plug the value in the equation. Okay, so if I can further simplify it, so this equation we can also write like this for velocity. Velocity is equal to under root 2 stagnation pressure minus p naught divided by rho naught. Okay, so I have just simplified this equation. So we have the value of stagnation pressure, we have the value of pressure at initial point, and rho naught we have just fine. Okay, so simply you have to plug the value and you will get the velocity of the aircraft, and this will be equal to 348.7 meter per second. Okay, so this is our answer. So if you have any question, you can ask, you can note it down. Okay, so now the question which you have to solve is the same. Just I am going to change some data. So here it is minus 18 degrees Celsius. This you can take as 178.5, and you can change this as 1500 kilometer per hour. So you have to send it to me by tomorrow or either within this week, and you will get 0.2 absolute mark for it. So if you have any question, you can ask me, and then we will stop at this point.
500 किलोमीटर पर आवर पे करना है.
1500 kilometer per hour.
ओके सर.